powerful tool, not necessarily that can be applied in this problem, but always try to think in those terms. So this is a problem wherein it is given that there are n participants in a meeting. Among any group of four participants, there is one who knows the other three members of a group. Prove there is one participant who knows all other participants. So let me model this solution. Let me model the question on a graph. So let's come to this and let's make a representation of the problem. So we are given there are n participants and any group of four participants, there is one who knows the other three members of a group. So let us consider we have it's some color. Let's assume we have got some four participants. Sorry for the bad, but yeah. So let's say that these are four participants and there exists at least one participant who knows the other three. That means there is one participant which has edges. So consider an edge between two participants as a connection between them. That means they know each other. So basically, if I consider this participant, that is the first participant, to know everyone else, then basically you get this kind of a situation where there is at least one part, there is one, it's not at least, there is one participant who knows the other three participants. Now you are given that there are n participants, and among those n participants, you have to basically find out, you have to prove at least one participant knows every other participant. So this is how you have to, like, there are, suppose there are, there is another vertex and you have to consider that, you have to prove that, suppose this is a vertex which is, or any of one of the vertex is connected to all other vertices. I hope the problem is clear. You can try thinking for small graphs and try extending it for larger graphs, or perhaps try to prove it by contradiction. So if you haven't been able to get away, let me try giving you some hints so that you can. Um,
I've actually come to like a rough solution to this.
okay, so can you describe it?
I mean, it's a bit inductive in nature. So let's say that if this is true for n vertices, so for n plus 1, suppose we add the extra point and initially suppose it's isolated from the endpoints. So among those original endpoints, there must be one point inductively which is connected to each of the n minus 1 points in the original graph. So then we can actually make cases while taking 2 points in the original graph, this point which is connected to all the other vertices and this isolated point. And then using that, you can actually show that there must be one more point for n plus 1 also.
Okay, yeah, this is also a very similar proof which I am going to describe. So basically, I'm also going to do something very similar. What I'm going to do is I'm going to assume that there is a vertex which is connected to all the other vertices by an edge. And then I will prove that if this is not the case, then suppose there is a particular vertex which is not connected to this particular vertex. So suppose I consider A is my vertex which is connected to all other vertices except one vertex B. Then there is, it's given that, it's given that we are having every pair of, so we are having that every pair of every set of four vertices, one knows all the other three. So basically, suppose I have some vertices which are in the neighborhood. So we know that all the edges, all the vertices which are adjacent to A are in the neighborhood of A, which is denoted by n of A. So we can do this, that suppose, uh, so obviously by our assumption, A is having an edge connected to all the vertices here. And suppose and any two vertices, suppose I consider this and this. We know that among these four set of vertices, there has to be one vertex which is connected to all the other three. And we know A and B cannot be them because A and B are themselves not connected to each other. So A is not known to B and neither B is known to A. So they can be only among these two. So for that, these two vertices have to be connected to each other. Otherwise, there cannot be a vertex which knows all three. So A is connected to this, and by our induction, by the statement of the problem, this vertex also should be connected to B because it should, suppose this is the vertex which is connected to all three. So it is connected to A, it is connected to B, and it is connected to the other vertex in the neighborhood of A. So we are able to prove one thing, that every pair of vertex in the neighborhood of A are adjacent to each other. Because if we connect them, we have to connect them. Otherwise, we cannot get a vertex which is having connections with the other three vertices. So since we are able to get this, then we can basically uh, prove that uh, suppose I consider this vertex and I consider its its pairs with other vertexes in the neighborhood of A. So basically this vertex is connected to A, this vertex is also connected to B, and this vertex is also connected to all the other vertices in the neighborhood of A. So that means this vertex is connected to all the vertices in this graph. Therefore, we are getting a contradiction. Basically, what our assumption was that this is a vertex which is of max. Basically, if we want to prove that there is no vertex that contains that is connected to all vertices, that is what is not being proved here. Because if we consider that this vertex is of maximum degree and is not connected to B, then we get some vertex in the neighborhood of A which is connected to B. So basically, this is not a maximum degree vertex, and so our assumption is false. And therefore, the maximum degree vertex has to be connected to all the other vertices in the graph. So I hope the proof is clear. And if you have any doubts, you can ask. So is it clear?
Yeah, it's clear.
Okay. So this one, I won't discuss it immediately now. You can keep thinking. So this is the problem. Basically, mm, this says that for the previous problem, prove at least n minus 3 vertices follow that property. So this is something which you can keep thinking, and if there is a time at the end, we can discuss it, or you can, uh, uh, yeah, we can discuss it if there is time at the end, or I will post its solution. So let's move on to the next problem. This is a very simple question. So that every simple graph has two vertices of the same degree. So anyone who can quickly answer this?
This was covered in the last class.
Yeah, this was covered in the last class. So I hope everyone knows its solution. So basically, we have basically n choices, and we have actually n minus one choices, and we have n vertices. So at least two of the vertices have to have the same degree. Because it is a simple graph, there cannot be any loops, there cannot be any multi edges. So let's move on to the next question. Again, this is very simple. So it's saying that if the distance UV between two vertices U and V that can be connected by a path in a graph is defined to be the length of the shortest path connecting them, then prove that the distance function satisfies the triangle inequality. Distance of U to V and distance of V to W is greater than equal to distance of U to W. So basically what it's saying is that if you have a case where UV is DUV is distance between two vertices uh, along the shortest path. So that is actually the length of the shortest path. So basically if you have say U and W, then DUW is the length of the shortest path between them, and there is another vertex V, and suppose UV and VW. So basically, we need to prove that this is true always. So can you give it quickly? Because this is very
I have
trivial.
a query on this. Like, what do you mean by the length of the path?
Basically, it means the number of edges. Because I am considering undirected graph, so each edge is contributing as value 1 to the length. Means if I gave a No, I'm giving a undirected graph or directed graph. That doesn't matter. I'm giving you a unweighted graph. So basically, we are only considering the number of edges that are in the path. Not that if I consider that I give a weight of 10 and if I give a weight of 5, then the length can be expressed as 10 plus 5, which is 15. But here it's like only the number of edges. So I think you must have got the solution. So basically, what we are doing is if d of uv and d of uw, just a second. Uh, Sorry for the disturbance. So basically, the proof is simple that UVW, basically, we are considering that U to W is a shortest path. So if distance of U to V plus distance of V to W is less than distance of U to W, then the shortest path from U to W contains V, means U to W, the whatever we are considering as shortest path is not the shortest path. There is a path shorter than this, that is from U to V and from V to W. So basically the assumption, the definition fails, and therefore this has to hold that distance of U to V plus distance of V to W is greater than equal to distance of U to W. So I guess this is simple. Let's come on to the next question. So this is problem 5. prove that if u is a vertex of odd degree in a graph, then there exists a path from u to v where v also has odd degree. So basically, it is telling that suppose u is a vertex, v is a vertex. We are not sure whether v exists or not. We have to prove v exists. We know that u exists. U is a vertex, u is a graph which is of odd degree and it exists. And therefore, v is a graph. We have to prove that there exists an edge which is basically also of odd degree and has been connected to u, means there is a path from u to v. So I hope the question is clear. Let me repeat it again. So basically you have an edge u and you have an edge v. You are not, I'm very sorry, I'm just making the same mistake. I'm not sure whether v exists or not. So I have an edge u and it is of odd degree. And all that I need to prove is there exists a vertex v such that there is a path from u to v and v has odd degree. So I hope the question is clear. So let's try to, has any one of you got any approach?
Like existence of V is guaranteed by counting the number of edges. Like if
How do
we
you
sum up,
guarantee the path exists?
Like if there's no path between them, then the given graph should be two independent graphs which are like not connected to each other.
And so,
And number of vertices having odd edges, I mean odd degrees should be even in number. And both of these new isolated graphs will have only one vertex with odd degree, which is not possible.
so both of these isolated graphs means have to have an even number of edge vertices which are of odd degree. So basically, you can consider that u and v will be in the same connected component. Means in a particular connected component, there has to be an even number of vertices which have the same degree. So I guess this is very simple. I mean, it's the way to do this. So basically, you have a vertex U and a vertex V, and what you're doing is it's simple that basically the number of edges, each edge is connected to two vertices. So we have already proved that sum of degree of vertices in a graph is even. The parity is even. So therefore, we can also move on here and say that the degree of this is odd. Then this degree also has to be, basically there has to be another vertex which has odd degree. But we should not proceed in this. We should first prove that we are guaranteed. We should try to modify this basically result that degree of degree of edge, sum of degree of vertices is even in each connected component. So basically there is a connected component, there is another connected component, and there are vertices in this connected component. Then basically the so basically this is an independent graph you can consider, and this is an independent graph. So sum of degree and this also has to be even. So if this is of odd degree, then this is also of odd degree. And since they are in the same connected component, by definition, there must exist a path between them. And so they are basically connected by a path, and also their degrees are odd. So basically, this is how we prove this. So let's go forward. So since we have a little bit of time, I would ask you to think on this. A graph is bipartite if and only if it contains no odd cycle. Remember that, recall what is a bipartite graph. That is actually a graph which can be broken down into two independent sets, wherein in each set the vertices are not connected to, means they are not adjacent to each other, and the only edges exist from a set to another set.
in this, like, hello,
Hello, yes, you are audible.
like we can just take the odd cycle and start distributing the points like consecutively. So we'll just end up with the last point that can go in any of the sets.
Could you repeat it again? We can just.
Like we will take the odd cycle, like the
Yes.
cycle of the points. Then we will just start distributing the points upon, like the adjacent point cannot be in the same set of that, like suppose A, B, C, D, E.
Yeah, yeah.
So we'll end up with the last point that can't go in any of the sets.
But okay. But you are not able to basically. You are saying that if it contains an odd cycle, it cannot be bipartite, right? But you are not
Yes.
proving that if it
These
is
are the
bipartite,
only
it
left.
does not. Yeah, you are not proving it in the other direction.
Okay, like, time the next, the other direction.
I mean, like if we have a bipartite graph, then suppose A and B are the two sets among which there are connections. So, like if we have a cycle, then the last point and the first point should be in different sets A and B.
No,
And
basically it is a cycle, so they should be in the same set, right? Means
yeah,
the means I mean the last and means the last means the basically you want to say that it is basically suppose if you have a cycle, then it has to be of even means it has to have even number of edges, because if you consider a cycle, then you have to come back to the original vertex, and so if you have to come back, then you have to at least travel to the other set and come back from the other set to this set. So you are actually traveling even number of edges to come back to the original graph.
yeah, exactly. Like
I
the
mean, it's
last
original
point
set.
should be in
Yeah.
the different set.
Yeah, the last point means, yeah, yeah, you can say that. The last point before we reach the starting point has to be in a different set. Yes. And therefore, we can prove that it is having even number of edges, and therefore any cycle in a bipartite graph has to have even number of edges. And also we are able to prove that if it is having an odd cycle, it cannot be a bipartite graph. So we are able to prove it in both directions. So let's think of another problem, which is problem this one. In the previous problem that is on this, we are proving only that one participant knows all other participants. Here you have to prove that at least n minus 3 participants or vertices follow that property. That means they know the other participants.
Like in this, we can show like we cannot have 4 points such that they like none of them like know each other because of the statement of the question. Then we'll just take 3 points like such that none of them know each other, and then we will take 1 point at a time and just prove. And then we'll take 2 points and we'll prove that all the n minus 3 points are connected to all the other points.
So yeah, you are saying this that they are not connected to each other and mm, at least n minus 3. So. But you are able to, okay, at least, yeah, n minus 3 means it can be greater than it. Mm, yeah, F3 don't. But you are, you are, yeah, you are considering a worst case and you are basically, but, yeah. This is a special, but actually, isn't this a special case, right? Because you are considering a particular graph. In general, can you prove this? Maybe I can get a tighter upper bound. Maybe I can write at least n minus 2 vertices follow that property. Mm, so means it's ambiguous here, but obviously I think you can just get a generalized proof so that it's like uh, coming as a tight bound.
I was just saying for the at least version, like n minus 3 is possible. I'm saying like n minus 4 is not possible, but n minus 3 is possible.
Yeah, n minus 4 is going to be even lesser. So yeah, n minus 3 you proved that yeah, you proved that if yeah, you proved, but okay, you are saying that you take three vertices which are not connected to a particular vertex, right? And uh, the other vertices have to be connected to these three or something like that. Could you repeat it again? I'm just getting a little confused.
Like I said, like consider the three vertices, like such that they are not connected amongst each other. So
Yes. Not
and then
connected
we will,
amongst each other means that there is no edge between any pair of vertices.
yeah, there's no edge.
Okay. So all three are isolated.
Hmm.
Okay.
So then I will just take 2 points from the n minus 3 set and 2 points from these three vertices, and then I'll prove that the other 2 points which are in the n minus 3 are connected to these two and the other point as well taken from the n minus 3. So in
Okay.
that way I can prove like those all n minus 3 is connected to all the other points.
Hmm. Yeah, I think this is right. Um, Let me tell you what I had as a proof. So basically, what I was actually going to do is consider that you have the same construction as before. Um, so basically, in the first, let's go here. In the first problem, we just had some construction like this. So here you can see that if A is not adjacent to B, then neither B nor A is complete. but this is complete. I mean, this is, I'm sorry, I should say that neither A nor B is connected to other vertices, but this vertex is connected to the other vertices. So, suppose I can just show this, that I can just show this that suppose this vertex is connected to other vertices. I mean, this is a vertex which is adjacent to A and adjacent to B. Means we considered, I'm very sorry for this, we considered a particular case of four vertices, and we got that this vertex is the one which is connected to all the others. And this vertex is not connected to either of A or to B or to both A and B. Doesn't matter. It's anyway not connected to all vertices. And now we take any other vertex in the neighborhood of A with this and A and B, and we still prove that this vertex is connected to all other vertices. So every other vertex in the neighborhood of A except this vertex is connected to other vertices. So basically, n of A minus 1 vertices are complete. So basically n of A was n minus 2 and minus 1 becomes n minus 3. So I'm able to prove that no less than n minus 3 vertices are going to be connected to all other vertices in the graph. So I think what you gave also is making sense. So if this is clear, let's get to another problem. This one I won't be discussing. I would ask you to think. If you are able to think it immediately within 2 minutes, we can discuss it. So the question is that a graph with at least three vertices is connected if and only if at least two of the subgraphs obtained by deleting one of its vertices is connected. So there is a graph which is having more than three vertices, and we have to prove that it is connected if and only if at least two of the subgraphs obtained by deleting one of the one of its vertices is connected. So basically, if you delete any vertex, then you obtain two subgraphs, and you have to prove that uh, any vertex, any means if you delete a vertex, then the two subgraphs that you obtain are always connected. That means suppose you have this and you have this vertex, and basically they are always connected. Always connected means that um, so basically the question is saying that if I delete the edge, I will obtain subgraphs, and these two subgraphs basically should be connected to each other through some other means. Like it's not that it's if I delete this edge, then this becomes like some disconnected or something. At least two of the subgraphs obtained by deleting one of its vertices is connected. Um, okay, let's see this. I think I made a mistake. At least three is at least. Acha, we are not doing this.
I think the question is saying that the two
Yeah. The
subgraphs
question
obtained.
is saying something else. I think it means that you have a graph, some graph, and you are deleting any vertex, and you are getting a subgraph, and at least two of those subgraphs have to be connected. At least two of these subgraphs obtained by deleting one of its vertices connected means you know that how you obtain a subgraph if you delete a vertex. So basically, at least two of them have to be connected. So basically, you can delete. You have n ways to delete a vertex, and basically you will get correspondingly n subgraphs, and at least two of them have to be connected. That is how you can prove the graph itself is connected. I think we should keep this as a homework. It may take a little longer for you to come up with an exact solution. So we will keep it as a homework, and I will also share with you three different PPTs, three different documents which contain exciting means a good amount of problems on graph theory, which you can go through. They are really good. Because of time crunch, I won't be able to extend this any longer. Anyway, I am done with all of the problems that I decided on except this, which also I will post the solution immediately within today, the solution in MS Teams, and you can check out if you are thinking which you thought now is like you are able to explain or understand the proof of this. So, so thank you for attending this session, and sorry for this disturbance. I did not have a proper sound system, so I could not control the noise. I will make sure that this doesn't happen in the future. And so we keep this as a homework problem, and probably we will plan another session on graph problems only. And yeah, we will try to cover more problems in that session. So it's this much for today. Thank you all for attending. If you have any queries, you can ask any small query or anything which you want to, or any feedback which you want to convey.